All right, so welcome back. Um, welcome back to this channel. So, in the last video, we have looked at LLM for recommended systems. Anyway, so in this video, uh, over the last few videos, we have been learning a lot of language modeling. We have been going into the world and learning about a lot of models and learn. We have also learned about a lot of techniques, right, to decrease cost computation, or computation cost while running language models. We have learned about flash retention, I believe, and also some other techniques maybe. Um, I have produced some videos, and if you want to just check out, maybe if you're interested in like decreasing the complexity of maybe language models, definitely check out. So, in this video, we are going to read this paper called FrugalGPT, right? FRUGALGPT. And we are going to. It is wrote by Stanford University, by the way. They have wrote this paper, and we will be trying to understand this paper. And this paper does produce some does provide some intelligent methods, intelligent things that actually work. Right? These people have already experimented these results or experimented these changes on actual language models, and they have found results. That is why they have produced it as a paper. So we're trying to read this paper and also just trying to understand what all the techniques and why they work, right? So let's just go through this paper. I think even I haven't read this. I'm going to read it with you, such that even you could understand how you could read a research paper, on how to approach a research paper. I'm going to get that thing straight to you. So reading research paper is actually quite intriguing, and it might make quite require a little bit attention, and a little focus from your side. So we'll be covering this. Uh, we'll be covering this paper so fastly as possible, and then we'll be going right. So I'm just going to we're going to read this paper. So again, the title of the paper is Frugal GPT. How to use large language models with while reducing cost and improving performance. Right. It's actually quite interesting title. I think we will be both reducing cost and also improving performance, which is quite. I think it normally would be kind of a trade off, right? When somebody were proposing methods to reducing cost, it will probably be a trade-off between cost and performance. Normally people would think that if you reduce the cost you might lose on performance. Well, this paper says and proclaims that they'll both reduce the cost and also improve the performance, which is actually quite interesting. And also the results are also quite interesting. If we as we go on this paper, we'll be reaching that also, we'll be seeing that also. Right, so let's read the paper, the abstract number one first. So there is a rapidly growing number of language models that users can query for a fee. We review the cost associated with querying popular LLM APIs, example ChatGPT, GPT-4, ChatGPT, J1 Jumbo, and find that these models have heterogeneous pricing structures. I'll just see what heterogeneous actually is. You know what? I'll just open ChatGPT, because while reading a research paper recently, I'll just have this ChatGPT beside, just to make sure that I understand all the words and all that. Even I don't know this word, so sorry. I just copy this. Heterogeneous is a term used to describe something consists of different or dissimilar elements. All right, so the prices are dissimilar. That means the prices are varying too much, right? Something that are varying too much. Maybe the prices are, maybe some models have a large price and some models have very low prices. So that is what they mean. There is a lot of variance in prices, right? Which fees that can differ by 2 orders of magnitude. In particular, using LLMs on large collection of queries and text can be expensive, of course. Motivated by this, we outline and discuss 3 types of strategies that users can exploit to reduce the inference cost associated with using LLM. So this paper mainly proposes three methods that we could use to reduce inference cost, not training cost, while using the model as an inference, while inference getting inference output. For example, after training, we would get the output, right? So while we are getting this output, they are going to propose a methods through which we could reduce the cost. And also, this Frugal GPT is built using these models, and they have found some very interesting and very attractive results. So the methods are prompt adaptation. Just keep these words in the back of your mind. It might now we'll soon study all of this. We'll soon understand all what these all means. Prompt adaptation. All right. LLM approximation and LLM cascade. Even I have no idea. I have absolutely no idea of what these even meant. Right. So we'll just learn about this as we go on. And of course, I'll try to make this video as fast as possible. As small as possible, because uh you know it's very hard to watch very boring video in which a boring guy is just talking a lot of boring things. So this isn't quite boring at all. I think this is actually quite interesting, this model. So yeah, we'll study. So these three, I think, strategies are used, right, to reduce the inference cost. To reduce the inference cost, these three strategies are basically used. So I'll just yeah, okay. Our experiments show that the Frugal GPT, right, we have Frugal GPT, right, can match the performance of the best individual LLM, example GPT-4. Wait a minute. GPT-4 by 4% with the same cost, right? We're going to have an accuracy. Okay, we are going to improve the accuracy of GPT by 4%, but with the same cost. The ideas and findings presented here lay a foundation for using LLM sustainably and efficiently, right? We are going to outperform GPT-4, not 3, by 4%, which is actually quite insane in my idea, right? And the ideas and findings presented here lay a foundation for using LLM sustainably and efficiently. All right. Introduction. We are in the midst of an explosion of LLMs, probabilities and all that. Why LLMs such as GPT-4 achieves unprecedented performance in tasks such as question answering, using them for high throughput applications can be very expensive. Right. So I'll just look it up in ChatGPT just to see what it means. I closed it. Yeah, I mean, definitely expected output, expected meaning, large volume of data, applications that are designed to process large amounts of data, right? So when we're dealing with large amounts of data, these prices are very expensive. For example, ChatGPT is estimated to cost over $700,000 per day to operate. Oh, that's some real huge money. $700,000 per day to operate. And using GPT-4 to support customer service can cost a small business over $21,000 a month. In addition to financial calls, using the largest LLMs ensure. I mean, just look at this numbers. They're going about like $700,000 per day, and also $21,000 per day for like small businesses. And they are not even talking like very, very, very high throughput applications like they have mentioned here. Even small businesses who are using like customer service will cost this much, and even ChatGPT takes like $700,000 per day to operate. Just inference, not even training. I mean, I thought even training would. I didn't thought even training would cost that money, but it's like pretty huge. Right. So yeah. I mean, it is a lot of money, right? In addition to the financial cost, using the largest LLMs ensures substantial environment and energy impact, affecting the social welfare of current and future generations. Right? it also leads to environment degradation. Of course, there are a lot of servers used, and there might be a little environment impact, but yeah, I mean, maybe they also do solve this in this paper. But anyway, the main thing is reducing cost. Right? How can we reduce the cost of this running of this model, inference of the model? How can we reduce the cost of inference by from using this model? Right. So just move on. So there are many LLMs now available via APIs, and they charge heterogeneous prices, varying prices. The cost of using an LLM API typically consists of three components, right? Three type of costs: prompt cost, right, proportional to the length of prompt. Of course, the higher the length of the prompt, let's say there's a lot of words in the prompt, it might cost a lot of price. Generation cost proportional to generation length. Number of words generated, I think, maybe the cost is proportional to the number of the length of the generated output. Three, sometimes a fixed cost per query. We compare the cost associated with using 12 different commercial LLMs from mainstream providers, include OpenAI, AI21, Cohere, and TextSynth. Their costs can differ up by up to 2 orders of magnitudes. For example, the prompt cost for 10 million tokens is $30 for OpenAI's GPT-4, but only $0.2 for GPTJ posted by TextSynth. Again, so here GPTJ is, I think, a smaller version of GPT. I think trained by TextSynth, right? It only costs like $0.2, whereas for GPT it costs $30 for 10 million tokens. Yeah, I think 10 million tokens is actually quite a huge number. Anyway, so there is a lot of variance, right? There is a lot of variance. Given the heterogeneous cost and quality, how to effectively and efficiently leverage a full set of LLM options is a key challenge for practitioners. If the tasks are relatively simple, then aggregating multiple responses from GPT-J offers performance similar to GPT-3. Right? If the aggregating multiple responses. So for simple tasks, GPT-J might work very good, right? For example, if the prompt is actually pretty simple, I think we could use GPT-J rather than GPT-3, because why GPT-J is cheaper, right, than GPT-3, and GPT-3 has like maybe more parameters and more things, whereas GPT-J is pretty cheap. And for simple prompts, it's quite natural to go to GPT-J and just look at this like variance, right? $30 and $0.2. I think a growth of about 5 into 30, 150, 150 times, right? GPT-J is 150 times lesser cost than GPT-4, and for simple prompts, it is of course better to use GPT-J, right? Moreover, relying on the API provider is not reliable. That if the provider becomes unavailable, potentially due to expiring demand. Existing model ensemble patterns such as Model Cascade and FrugalML were designed for productive tasks with a known set of labels and do not account for the full capabilities of LLM. How to use LLM affordably and accurately, therefore calls for new approaches. Right? We lay out our mission for a flexible framework that uses LLM APIs to process natural language queries within a budget constraint, termed FrugalGPT. Right. So these people are going to develop a framework that uses LLM APIs to process natural language queries with a budget within a budget constant. So they're going to set a budget in which they are going to process natural language queries. And the name of the model or the name of the framework is FrugalGPT. Right. So yeah, so as you can see in the diagram, I think the cost thing here, right? And just look at other models and look at FrugalGPT. Just look at the increase in like performance. It even like crosses ChatGPT-4. Of course, it uses GPT-4 in its thing, but this is the cost, by the way. Even for very less cost, you're going to get pretty good models. Like just look at this point. This is a pretty juicy point. There's not variance for each cost. Also, there is no need of using a model at this area. it's very pretty reasonable to use the model at maybe this area, maybe at this point, right, with very less cost and very good accuracy, right? I mean, it outperforms. Like I think it also outperforms GPT-4. Just look at the computation cost of GPT-4, probably around 35 or something, $35. Whereas for Frugal GPT, with just like $5 or $6, we could generate like 87. Yeah, of course, like similar to GPT-4, I think. So this is actually quite impressive, right? Our vision for reducing LLM cost while improving accuracy. So yeah, the standard usage sends queries to single LLM, which can be expensive. So this is expensive, they say, sending things to GPT-4 and getting an answer. Uh, our proposal is to use prompt adaptation, LLM approximation, LLM cascade to reduce inference cost by optimizing over the selection of different LLM APIs, as well as prompting strategies such as zero shot, few shot, and chain of thought. We can achieve substantial efficiency gains. Right. So here, I think they are going to use like multiple models. Even I don't have an idea. So based on what they have told here, I mean, I think they have separate section for like explaining all the things they have mentioned. But based on what they have mentioned here, I think they are going to use multiple language models, and yeah. So they're going to like select the best API thing, LLM API, based on the prompt, and also they're going to use like bunch of prompting strategies, through which they can achieve pretty good gains, let's say, right? Okay, so they're going to do this, and now we can just go on related works, prompt engineering. There are some related works, and I think a lot of works now has been in the field of reducing the inference cost of the language models. I think there have been many techniques that have been created. Number one, prompt engineering. Just making the prompt. Prompt engineering has emerged a discipline for crafting prompts to enhance LLM's performance of our application. Again, I think we could just skip this part. Whenever you are trying to read a research paper, you might get this related work section, which is perfectly fine to skip, because it may be like sometimes out of context also, so it is better to skip. I mean, at least for now. Maybe if you're interested, definitely check, definitely read that out. Right, scope and problem statement. Let's just read this. Natural language question query answering. In this paper, we concentrate on the standard natural language task, where the objective is to answer a question query K sample from a natural language query distribution Q. All right, I think we could just we'll just leave this. So yeah, we consider answering queries via the LLM market, which compromises K different LLM APIs denoted by this. Each FI P2A is a function that gives a prompt P, with that given a prompt P from a prompt space P generates an answer from the answer distribution A. Right. Note that to use LLM APIs, one has to convert each query Q to some prompt first. LLM APIs are associated with their own cost, typically consisting of three components: a portion proportional to the length, portion proportional to the generated answer, and sometimes a fixed cost per query. Right, I'll just skip this part. The cost is, I think, calculated by this formula, right? Where Cij are like constants. Yeah, so they are just constants, right? And an illustrative example, adapting the case study provided by COSA or something. Assume a small business operates a customer service using GPT-4. The company caters to 15,000 customers each month, with each customer asking 3 questions twice a week, totaling 360,000 queries per month. Suppose for each question, it's considering prompt average 18,000 tokens. And the answer is yeah. So they just calculated that the company said this small business might have to spend like $21,000 for like each month, per month. So they have to spend like $21,000, which is pretty high, right? The problem statement. Our primary goal in this paper is leveraging LLM API within a budget constraint Right. So the yeah is bounded by a spare user. Here, A denotes the correct answer. Okay, I'll just skip that. The reward function measures how closely the generated answer aligns with the correct one. It is crucial to note that the search space for this strategy is vast, encompassing factors such as which prompt to use, which LLM may be used to employ, and how to aggregate the responses. So basically, I'll just describe the problem statement to you. All I have read here, all we have read here, hopefully. So language models are pretty high cost. I mean, we have just saw a formula how to calculate it. I mean, it for like I think 300,000 prompts. It took like $21,000 each month, which is quite high, right? So these models are of very high expense. So therefore, we will be trying to in this paper. There we are going to try to build the method, build the methods. I think, and they have also specified the name previously. So we are going to use these methods to reduce the prompt cost. And we have shown that in the result section in the graph, we have shown that right in this so they have a graph here. I hope you have seen it, shown it, it's seen it, right? So we could get we could achieve the performance of almost GPT-4 with like very small cost using FrugalGPT. So right, let's see what methods we'll be using in order to build these models such that they are both affordable and also accurate and also up to the mark, right? So I think this is that section where we understand all the things that they will be doing, and we'll be going step by step, one by one. So please stick with me. I will just go up. Right, so we'll just look at this diagram first. So now we present our vision on how to use LLM's API within a budget. As shown in figure 1, we discussed 3 cost reduction techniques, namely prompt adaptation, LLM approximation, and LLM cascade. So we'll just look at these diagrams first and try to understand what is actually going on. Prompt selector, there is some prompt with like, I don't know what that is. Also, I think we have the same prompt, and then GPT, we are going to send that to GPT-4 and we're going to get the output. So I don't quite understand this prompt selection, but we'll just try to go on. Because we are going to have a separate explanation for that. Don't worry. And we have query concatenation. Right, we have one prompt. We have one prompt. What is the real result of N2 and O2 at high temperatures? And we also have another prompt. What helps spray height? And what we are going to do is we are going to concatenate, or we're going to create one whole string in which we are going to have both of these questions. So we're going to add these questions in like a string, and we're going to pass both of these questions to GPT-4 at the same time, and we're going to get the output for each of these prompt, which is actually quite interesting and quite simple, right? And it's actually very simply intuitional, right? Now, not huge lot of thought there, right? We're just going to concatenate prompts. We're going to add prompts. I'm going to send both of these prompts together to GPT-4, and we're going to get the output for both of these, for both of these values, for both of these prompts, right? And then completion cache, right? We're going to ask a question. I think we're going to have a cache or something, and then I think we have so I think this is actually quite similar. I think I'm going to guess what this means. I guess that we are going to have like a database in which like we store all the previous questions, and also we are going to have we are going to search for similar questions. So when asked the question, we are going to search for similar questions. Okay, so we are essentially going to like give it a prompt to the model, and the model is going to search for similar prompts and maybe for similar answers. Yeah, maybe the model already ran on, I think, a similar prompt. Then we already have the answer, right? So we're going to based on this answer, I think we are going to answer this question, and I think that's completion cache. And then model fine tuning. Yeah, I think model fine tuning is actually quite All right, so we're going to have some data. We're going to give that to GPT-4, and I think yeah. So we are going to have a expanded model and going to fine tune it on like a small model. I think, and the LLM cascade. I don't quite understand this, but however, we're going to move on. We're going to read the summary. We're going to read the uh, description that they have provided. All right, so let's go on. So prompt adaptation, let's see what that is. The strategy number one, the cost of an LM query increases linearly with the size of prompt. Consequently, a logical approach to reduce the cost of using LLM APIs involves decreasing the prompt size, a process we refer to as prompt adaptation. Prompt selection. Prompt selection is a natural example of prompt adaptation. Rather than employing a prompt containing numerous examples that demonstrate how to perform a task, right, one can retain a small subset of examples in the prompt. This results in smaller prompt and subsequently lower cost. An intriguing challenge of prompt selection lies in determining which examples to maintain for various queries without compromising task performance. All right. An additional, so what they have, I think, told here is that yeah, the lesser the size of the prompt, the more efficient the model actually is. The lesser the cost. Rather than employing a prompt containing numerous examples that demonstrate how to perform a task, one can retain a small subset of examples in the prompt. So yeah, I think we are going to like decrease the number of elements in the prompt, maybe just taking the most important words and sending that, I think, to the language model. I think that is what we are going to do. Right. And then an additional instantiation is query concatenation. Right. Again, I think I have, I mean, I have already said what that is. It is important to note that processing queries individually necessitates sending the same prompt to a LLM API multiple times. Therefore, the fundamental concept of query concatenation involves sending the prompt only once to the LLM API while allowing it to address multiple queries, thereby preventing redundant prompt processing. To accomplish this, several queries must be concatenated into single query, and the prompt must explicitly request the LLM API to process multiple queries. Right. For instance, to handle two queries using one output, the examples presented in the prompt can include both queries followed by their corresponding answers. Pretty intuitional, right? So what we are going to do is not just two prompts, but we are going to take multiple prompts and we are going to concatenate them into a single string. And then in the prompt, through the prompt, we'll just ask the model and we're just going to tell the model that these are different prompts. We are going to give an instruction to the model that these are different prompts, and the model is going to take in one prompt, and that one prompt is the sum of all the queries, and the model is going to answer to each of this query. Right. So each query will be answered by the model. And essentially we are going to like pass in the prompt. In the prompt, we are going to pass in a request to the language model to answer all the queries in the prompt, right? And yeah, we'll just use we're just going to use the prompt for that. So by using this, we could of course decrease the complexity, the computational cost required to answer all the queries, right? So that is query concatenation. Strategy 2, LLM approximation. The concept of LLM approximation is quite simple. If an LLM API is too costly to utilize, one can approximate it to using more affordable models or infrastructures. One example is completion cache, as depicted in figure 2. The fundamental idea involves storing the response locally in a cache when submitted a query to LLM API. To process a new query, we first verify if a similar query has been previously answered. If so, the response is retrieved from the cache. And an LLM API is invoked only if no similar query is discovered in this cache. The complete cache provides substantial cost savings when similar queries are frequently posted. For instance, consider a search engine. So basically, LLM approximation or completion cache. So yeah, as I have guessed and as we have predicted, completion cache means all the queries and all the answers that have been given by the model by the LLM will be stored in a database. right? And then in the database, whenever a new prompt is asked, right, whenever a new question is asked, we'll just verify if similar questions to the given query. So we are going to have a query, right? We're going to check if similar queries have been given, and if similar queries have been given, right? If similar queries have been given, we will just retrieve the answer that we have given to that similar query, right? For example, I say that my or let's say I ask who is the let's say who is the president of India, then the answer is going to Narendra Modi. And if someone asks that same question again, rather than producing or generating the output again by the LLM, we are going to use the saved output. Going to have the same saved output, and it's going to use this saved output to give the output. And we are going to have an algorithm, I think, to basically verify if two questions are equal, two questions are similar. I think we are going to use a machine learning algorithm or deep learning algorithm or a language model or even a basic NLP maybe classifier to predict if two queries are similar. It's pretty simple, right? Another example of LLM approximation is model fine-tuning. As shown in figure 2, this process consists of 3 steps. First, collect a powerful but expensive LLM APIs response to a few queries. Second, use the responses to fine-tune a smaller and more affordable AI model. And finally, employ the fine-tuned model for new queries. Right, simple, pretty simple, right? So essentially, we're going to have basically a powerful and expensive LLM. So for example, GPT-4, it's very powerful and maybe expensive. And we are going to use this GPT-4, and we're going to pass multiple prompts. We are going to pass multiple prompts to this GPT-4, and we're going to have multiple outputs for each of the prompt that we have passed to GPT-4. And essentially, we're going to take in all the prompts that we have passed to GPT-4 and all the answers that we have got from GPT-4, and we're going to fine tune a smaller model, let's say GPT-J, and we're going to fine tune this GPT-J on these outputs and on these inputs and outputs of GPT-4. So basically, we'll just fine tune this model, and we'll just update the weights, and we'll just take these queries and predict the output and have a loss function of that. That is fine tuning. That is model fine tuning. Strategy 3 is LLM cascade. So the increasing availability of LLM APIs with heterogeneous performance and cost presents a unique opportunity for data adaptive LLM selection. So basically, this paper has pressed on one point, one important point, and the point is that there are very heterogeneous prices. I mean, there's like a lot of variance between GPT models or language models. So there is a lot of difference on cost and performance on these language models, and so this provides us a unique opportunity to have a algorithm to select LLMs. Right? So basically, we don't know what LLM we should use for each prompt. I think that is what they are trying to convey. So LLM cascade, as illustrated in figure 2, is one such example. LLM cascade sends a query to a list of LLM APIs sequentially. Yeah, so I think we are going to have a bunch of LLM APIs sequentially. So first, we are going to maybe send this query maybe to the lowest model. Sorry, a model with the lowest computational cost, and then we are going to send that to a better, a higher or powerful model, a more powerful model. So where if one LLM API's response is reliable, then its response is returned, and no further LLMs in the list are needed. Right? So we are going to go through a bunch of these LLMs, right? So, and if the first LLM response is good, and we are not going to continue through the next LLM, right? So that is the thing. The remaining LLM APIs are queried only if the previous APIs generation are deemed insufficiently reliable. If the current LLM API's output is not reliable, then we are going to go through the next LLM, right? So basically, this might. So if you have just read this thing, or if you have heard this thing for the first time, you might say that this does not reduce the computational cost. I mean, we are running between like many applications. Sorry, many LLMs, right? We're going to have a bunch of LLMs. We are going to, like, let's say we have a complex query, right? We are going to go through all the LLM list. We're going to run one by one through all the LLMs APIs. And you might think that is bad, but to be honest, that is actually pretty good, because most often than not, uh, we're going to get like simple prompts, most probably, because humans, and and we know the one point that they have pressed in this paper is like, the cost of LLMs is like pretty heterogeneous. That is what they have pressed in this paper. So therefore, we are going to have this LLM API sequentially, and we are going to loop through and or go through each LLMs, and these LLMs are maintained in or arranged in ascending order based on power, on how powerful these LLMs are. And if we get simple prompts, we could just like stop at the first step, which is pretty low cost, right? Just look at the cost difference. GPTJ costs like $0.2, and GPT-4 costs like $30. A lot of price difference. And if you could like stop at the first or or the second or the third API, LLM API, we could have saved a lot of um cost, right? We could have saved a lot of cost. That is the key thing of LLM cascade. The key components of LLM cascade consists of two elements: a generation scoring function and an LLM router. The generation scoring function generates a reliability score given a query and an answer produced by LLM API. Right, so basically, we are going to have like two parts in this LLM cascade. The first part is generation scoring function. So when a answer is generated by one LLM in this list, we are going to pass this generated output to this function, to this generation scoring function, and this function is going to score the output of the model, or score the response of the model, right? And so that is the thing of that is what generation scoring function is doing. The LLM router selects LLM APIs to include in the list. Okay, I think LLM API router will just select like some APIs that should be included in the list. All right, so I think let's move on. So to update the scoring function, the scoring function can be updated by training a simple regression model. We could just train a simple regression model based on the previous data on how good some prompt is or some response is, and how bad one response is based on the prompt. So we're going to pass the prompt and the output, and we're going to have and we're going to have a score, right? We're going to have a bunch of these things as a training data, and we're going to train the model on that. A simple function regression model. Combining approaches across different strategies can lead to further cost reduction and performance enhancement. Yeah, so we could just use like bunch of these methods in a combined manner based on a problem, thus decreasing our that's decreasing our cost. I think that is the basic. I think that the most important and primary thing they have stressed on in this paper, I think. So I think we're just going to look at some graphs, and we'll be going on. So yeah, so we have a bunch of data sets here. So essentially, we have a bunch of data sets here. So one data set is headlines, and one data set is overruling and all that. So, and we could see the performance, and as you can see, FrugalGPT is almost like outperforming all these other models. So maybe in the case of overruling data set, GPT-4 is almost in the level of FrugalGPT, but still it is able to outperform GPT with like very less cost. We have to get there, and maybe this is Coca dataset did maybe this dataset has challenged this model a little bit, but still the model is actually performing quite well. So thanks for watching. I'll see you in the next one. So bye.